Whoa, where am I? I was just with my friends. Hello? Is anyone there?
Hello. You have been randomly selected and have been temporarily transported into a higher plane of existence with an added third dimension. You are a 3D character in a simulated environment that exists only in a computer, rendered and displayed for higher beings.
Wait, what?
One crash out later.
So how does it all work?
How does what work exactly?
You know, how am I a 3D model in your words, being projected and rendered onto a 2D screen?
To explain your question, we must first define some basic concepts. A vector is a quantity with both a magnitude and a direction. In computer graphics, vectors are three-dimensional, represented by how far along the x, y, and z axes the vector extends from the origin, also called components. Treating the endpoints of vectors as the location of vertices, 3D objects called meshes can be defined by connecting said vertices into edges and faces.
Wait, so I'm a mesh composed of faces and edges defined by vectors.
Correct. However, it may not be as simple as you imagine. We have only just defined what a mesh is relative to an origin for the mesh, known as mesh space. To continue, we must place meshes into the world and then determine what the world looks like from the perspective of the camera, as the camera will be in the center of the screen when displayed on the computer. In a nutshell, we need to convert the vectors defined in mesh space into the coordinate system of the world, known as world space, and then into the coordinate system of the camera, known as camera space. Since each space has a different coordinate system, the mesh does not exist at the same coordinates in each space. Thus, we must find how to convert them.
Okay, so how?
To do this, we need to introduce transformations. To move from one coordinate system to another, we need to manipulate the original mesh by scaling, rotating, and translating it. A transformation takes the original x, y, and z components and replaces them with new ones. For example, scaling a mesh can be accomplished by redefining the components in the same direction, but with a different magnitude. Rotation can also be achieved in a similar way by redefining the components of the vector to be in new directions. Finally, translation simply moves the vector to a different position, maintaining the same magnitude and direction.
That seems tedious. Is there a better way to keep track of the transformations?
Matrices.
What the heck are...
Matrices are a representation of the transformation of vectors. If you take...
My apologies, my sound card is on the fritz. If you take the new vectors you replace the components with and arrange them in a grid-like formation, you get a matrix. To scale a mesh to twice its size, you replace the components with double their original components. When you apply these new components to the original vector, you double its magnitude, and thus will have double the size of the mesh it defines. This is 3 times the size. This is half the size.
Stop doing that!
To rotate, you can redefine each component with a component of the same magnitude, but in a different direction. For example, to rotate 90 degrees clockwise around the z-axis, you replace the x and y component like so, and keep the z component the same. Visually, you are turning the x-axis into the y-axis, and the y-axis into the negative x-axis. Once you apply this to the original vector, you get a rotation. Want to rotate?
Not really.
90-degree rotation clockwise around the z-axis.
Ah! Oh, that wasn't that bad.
135-degree rotation counterclockwise along the x-axis.
Stop!
You can combine these two types of transformations into a single matrix by applying the transformations of one matrix onto the components of another. Now, by applying this combined matrix, you can scale and rotate any 3D mesh at the same time.
Wait, I don't want to... Can you stop?
Unfortunately, translations are less intuitive. They require a 4x4 matrix, as our goal is to add a vector to the final product of the transformation, which is impossible with our current matrix. We currently do not have the time to cover this in detail, as our time together is nearly expired.
Thank goodness. So what happens after all the transformations are done, and we are in camera space?
A final transformation, known as a projection transformation, projects the image onto the plane representing the screen. This can be done several different ways, but the final product is that the 3D environment is displayed onto the 2D screen. That concludes the time we have together. You may now return to your friends in your world.
Wait, one last question. This is just for this world, right? So then why did these higher beings put so much effort into making all of this just for this 3D stuff? It's almost as if...
Incorrect. The use of matrices in rendering is fundamental to all forms of 3D rendering. There are other worlds like this one, all constructed to complete tasks ranging from design, to video games, to entertainment. This world is not unique.
Wait, what? We're not alone? What else is out there? Who?
That is all the time we have. You will be sent back to your 2D world shortly. Farewell.
Wait, but I just learned that there's more than just my world. What do you mean? You can't leave me like...